Okay, so one of the advantages of studying the basic principles of quantum mechanics in terms of qubits is that it makes things much simpler, and you can actually get to fairly interesting concepts in quantum physics very quickly. So what I'll do is go through a very simple explanation in the setting of qubits of the uncertainty principle. Okay, so what's the uncertainty principle? I'm sure some of you have heard about it already. This was discovered by Werner Heisenberg. It's called the Heisenberg's uncertainty principle. And the most common usage of it is with respect to position and velocity. So what Heisenberg discovered is that in quantum mechanics, you cannot really pinpoint both the position and the velocity of a particle with perfect precision. So if you know its position perfectly, then you end up being very, very uncertain about its velocity. And if you know its velocity, then you end up being very uncertain about its position. And what you can do is you can try to narrow down both, but then there's a limit to how well you know each of them. And that's this uncertainty principle, which says the uncertainty in the position times the uncertainty in the velocity is at least some quantity. Okay, so now what we're going to do is we're going to study an analogous principle, uncertainty principle for qubits. Okay, and what this is going to do is it's going to illustrate the basic principles. Why is there an uncertainty principle at all for position and velocity? Well, we'll look at that later in the semester, but for now, in the context of qubits, we're going to look at these two quantities. So remember, our qubit is the state of this electron in a hydrogen atom, ground or excited, and we might want to measure the bit, whether the qubit is in the state 0 or 1. Of course, the bit has a physical interpretation. It's the energy of this. It corresponds to the energy, whether it's in the ground state or in an excited state, whether the energy is low or high. We could also measure a different quantity, the sign, whether the qubit is in state plus or minus. Okay. These are strange states of this electron, but you could imagine that this could have some physical meaning. So let's pretend for the moment that these are two different physical quantities that we are interested in, the bit and the sign. Okay, so we could ask the question, can we know both the bit and the sign of a qubit with perfect precision? So what do I mean by this? So let's say that we have our qubit, it's in the state psi, which is alpha 0, 0 plus alpha 1, 1. So now, what's its bit value? Well, we know that if we were to do a measurement, it would be in the state 0 with probability alpha naught squared, and in the state 1 with probability alpha 1 squared. And so if alpha naught and alpha 1 are both non-zero, then we'd be somewhat uncertain about the actual bit value. So the only way to be perfectly sure about the bit value is if either alpha 0 equal to 1 or if alpha 1 equal to 1. So there are only two possible states of this qubit where we'd be perfectly certain about the bit value. If it's either in the state 0 or in the state 1. Okay, so this is for the bit value of the qubit. But now suppose we were interested in the sign. Well, then we could write psi as beta 0 plus beta 1 minus. And now if we were to again measure, we'd see it in the plus state with probability beta naught squared and minus with probability beta 1 squared. Again, if we want to be certain about the sign value, the only way this could be is if beta naught is 1 or if beta 1 is 1, which is the same thing as saying if it's either in the state plus or in the state minus. But now, what if the qubit was in the state plus? How certain would we be about the bit value? Well, the answer is, if it was in the state plus, then we are maximally uncertain about the bit value. Because if we were to measure it in the bit basis, we'd get 50-50, 0 and 1. And so what this tells us is that the bit basis and the sign basis are incompatible with each other. If you are certain about one, then you are maximally uncertain about the other, and vice versa. And this is the origin of the uncertainty principle. It turns out that the bit and the sign bases are Fourier transforms of each other. This is something we'll talk about later. So, it's just to give you a heads up. And in a similar way, the position and the velocity are Fourier transforms of each other. And so the uncertainty principle just comes from the fact that these two bases are incompatible with each other. They're maximally far from each other. Okay, so here's a way you can actually quantify this. So we can define the spread of a quantum state. So if our state psi is written like this in the standard basis and like this in the sign basis. And now let's define the spread in the standard basis to be the absolute value of alpha naught plus the absolute value of alpha 1. And similarly, the spread in the sign basis is just the absolute value of beta naught plus beta 1. So now let's look at the spread for the basis state 0. Well, in this case, alpha naught is 1 and alpha 1 is 0, and so the spread is 1. But on the other hand, its spread, if you look at the plus state, its spread is, well, the plus state is 1 over square root 2, 1 over square root 2, so its spread is 1 over square root 2 plus 1 over square root 2, which is square root of 2. So it has a large spread. On the other hand, if we were to look at the spread in the sign basis, then the spread of the 0 state in the sign basis, well, in the sign basis, the 0 state looks like 1 over square root 2, 1 over square root 2. And so its spread is large, it's square root 2. Whereas in the sign basis, the spread of the plus state, well, that's just beta not equal to 1, beta 1 equal to 0. So its spread is just 1. So what this shows is that what you can do is you can try to make the spread in the standard basis small, say by using the 0 state, but then the spread in the sign basis becomes large. It becomes as large as square root 2. On the other hand, you can try to make the spread small in the sign basis, but then it becomes large in the standard basis. And in fact, the spread is always between 1 and square root 2. And so what you can show is that no matter what state you pick, no matter what alpha naught, alpha 1 are, beta naught, beta 1, the spread in the standard basis times the spread in the sign basis is always at least square root 2 for any state psi. Okay, so this shows that there's going to be uncertainty. No matter what you do, you can just trade off the uncertainty in the bit and the sign. So that's a very, very simple illustration of the uncertainty principle in this context of qubits.